class, I wanted to take some time to do a little bit of review of filtering in Matlab and kind of how that works and how we can use the WMAfilter to do that, and then just some of the basics of signal processing. So I made a short script that generates some different signals, adds them together, and then passes them through the WMA filter. And I want to talk a little bit about how that works, kind of how we can know what's going on with these signals, and kind of some of the limitations of what we're looking at, right? So first things first, this script generates a time vector. I'm just using this as time, and it goes from 0 in 0.01 second increments to 10. So this is a 100 hertz signal or sampling frequency. So all the samples that I'm generating are going to be generated at 100 hertz. That's the time interval that I'm using. It's important that I know that sampling frequency before I apply any discrete filters, because the discrete filters generally do not know at which frequency the sample is collected at. So you have to convert whatever cutoff you want into kind of the same domain as the samples are initially. Here I have parameters for an initial signal. I've got an amplitude in volts. I've got a frequency in hertz. I also have a phase offset. I'm actually not using the phase offset right now, but I wanted to include that in case you wanted to play with this and see how changing the phase of the signal changes the results. It's not going to have a significant impact overall, but it will change how things look and how things behave to some extent, especially if the signals are very close together in frequency. If you have two signals of the same frequency and you add them together, you're not going to change the frequency, but you're going to change the amplitude of that signal. So as those signal frequencies get closer together, the net amplitude will change more. So feel free to play with that if you like. So this first signal here, we just have the amplitude. Again, this multiplied times sine of the frequency times 2 pi. Again, we're converting frequency into hertz into frequency in rads per second with that. And then we multiply times seconds, we get radians. So that works out just fine. And then, as we can see that in the plots here, so this is our signal 1. It's got a frequency of 2 hertz, which means that every second it oscillates twice, right? So it's twice per second. So if I look here to 2 seconds, I can see it goes 1, 2, 3, 4 times before it gets to 2 seconds. And then the second signal here, we've got a frequency of 0.5, and they both have the amplitude of 4, so you can see the amplitude on both these signals is 4. In this one, we get 1 cycle in 2 seconds. So it's got a period of 2 seconds, a frequency of 0.5. Kind of pausing just to think about this before I talk too quickly. I don't want to misspeak. Again, same exact equation I have for sample 2 as I do for signal 2 as I do for signal 1. Just using the amplitude and frequency of the sample 2 parameters as opposed to the sample 1 parameters. And again, I'm just plotting these with the different labels. I'm using an XY plot using the time vector t as the x-axis, and then the signal itself as the y-axis on those plots. So hopefully that makes sense. I'm also using the axis command to make sure that all of these axes have the same x and y range to make it easier to compare the different signals and the signal after filtering. This next one here, this third plot on the bottom left, that is the combined signal. So it's really just the sum of signal 1 plus signal 2. And you can kind of see the low frequency component in this as well as the high frequency component. And if I wanted to, I could get a reasonable approximation of the period of each of these just by looking at this graph. Again, I can use my traces here to look at multiple points on this. And if I look at that, I can see that this signal has returned to kind of its initial spot, right? So it kind of went through one oscillation in about 0.5 seconds, right? Which, again, is what I expected to do, right? You should have a oscillatory period, right, of a half a second if its frequency is 2 hertz. And if I move these around, I can find 2 points where it repeats for the lower frequency component, and it's going from 0.6 to 2.6. So again, it's got a period of 2 seconds. So I can look at this combined signal and I can get an idea for what the component signals are. It's a little hard to see exactly because again they're intermixing with each other, and that can skew the data a little bit to one side or the other. Again, especially if those frequencies are close together. So hopefully you can see that and that makes sense. The fourth plot that I have here is the filtered signal. Right now I have this using a low pass, or sorry, this is actually a high pass filter. So this is a high pass, I should label this high pass filter, because I'm actually subtracting the low pass filter results from the signal data. Let me change this back to the low pass filter. So here I converted the cutoff frequency into my frames. The way I did that is I have a parameter here, which is the cutoff frequency I want in hertz. I convert that to a period in seconds by taking the inverse, right? So the inverse of hertz is seconds, and then I multiply that times the sampling frequency. In this case, we have 100 samples per second. And so in this case, if I want a cutoff frequency of 1 hertz, I have a sampling window for my filter of 100 frames. You can see that when I do that and I put this into the WMAfilter, I had to transpose this signal because I generated all of these as a row vector, and the WMAfilter is designed to use our qualsys data, which is all column vectors. So I transposed the signal going into that as well as the signal coming out of that, just so it would be consistent with the other signals that I'm generating. Again, you can look at that in Matlab if you want to play around with those values. But you can see that when I run this through the WMAfilter with that cutoff frequency of 1 hertz, I get something that is pretty similar to the lower frequency signal. It's been attenuated a little bit, so it doesn't get to quite this maximum peak as it was before. I do have, pretty close to my cutoff frequency, 2 hertz versus 1 hertz, but it is being preserved as it's going through there. And there's some artifact by the original portion of the signal, because that WMAfilter is less effective, where it's not able to apply the window in both directions around the current data point time, right? So there's some artifact there. But we can see that this signal here looks pretty much like this signal down here, and it is doing a reasonably good job of filtering that data. Again, if I want to switch this to a high pass filter, all I need to do is take the original data and subtract the low pass filter results, and I can just change this to plot that. So I'll just change this to high pass, and we can see that this signal here now looks like this one down here, that's got that larger frequency, that 2 hertz frequency, right, or that 0.5 second period, and it's mostly being preserved. There's a little bit of that low frequency oscillation still in there, and probably a little bit of this signal on the high frequency piece is getting attenuated to some extent, but you can tell that this one here looks like this one, and so I can pull that apart. Hopefully that makes sense. If you guys have questions, feel free to let me know, and I'm hoping this will allow you to use these discrete filters to process your data in a meaningful way. Have a good afternoon.